All right, so this lesson is 2-5. We're going to be talking about inverse functions. So we're going to start on page 19 in your packet, but we're going to actually flip through some different pages so that we can get a better understanding of what an actual inverse is. So I'm going to share my screen with you. All right, so first of all, what you need to know about an inverse function is that an inverse function is basically where you're taking the x and the y value and you're swapping places. Okay, so if I was looking at a table or something like that, and if I started out with 2, 4, 1, 0, -5, -8, then the inverse, everything would literally switch places. All right, so the inverse function would be the 4, 2, they'd swap places, 0, 1, because they swap places, and -8, -5, again, because they swap places. All right, so when we're looking at inverses, we're going to be swapping the x and the y, but we're going to have to actually do some algebra with this, all right? But then you're going to end up solving for the y, and then you'll just rewrite it in inverse notation. All right, so those are some of the basic steps to finding an inverse. All right, but first I already kind of briefed you through the table type scenario. So this is on page 22 in your packet. All right, but the learning target here is being able to read the values of an inverse function from both a graph and a table. So we're going to start off with a table, but then we're going to kind of move towards the graphs. All right, so based on the example that I just showed, all right, if we take a look at this first table right here, you know, which one of these two tables would represent the inverse? So remember what I said, the x's and the y's do what? They switch, right? They just flip-flop. So here we start out with -2, 0. That means we would have to have 0, -2. Well, that's right here. We start out with -1, 2. So if we flip-flop to -1 here and so on. All right, so these two functions actually represent inverse functions from within a table. So that's how you can tell if two functions are inverses, by looking at a table. You literally look at the x's and the y's, and they switch places. All right, now when I'm saying y's, I do want to remind you that f of x and g of x and h of x, that's another way of writing y. It's just sometimes, you know, if you're trying to represent different functions, like a profit function or a revenue function, a cost function, sometimes you represent it with letters instead, like c of x, p of x. Instead of saying y, because you can't just use y for every single function. People might get confused about which one you're talking about. All right, so that's why they do that. All right, so that's looking at a table. So with a graph, the same thing happens. All right, the x's and the y's switch. So the first thing you want to do if you are drawing an inverse function is you want to figure out what your original points are, and then switch the x and the y, and then plot the new points. All right, so if we look at the left side, then this point over here is -2, -4. All right, so if I switch that, that would be -4, -2. So I'd plot my point right there. This next point is 0, -3. So if I flip that, it'd be -3, 0. And then I can keep doing that for all the points, but since this is a line, I'm just going to skip over here to 4, -1. And if I switch those, I'd get -1, +4. All right. And then if I do the best I can, I'm kind of doing it on my screen, to connect those dots, then I end up with a line that looks something like that. So that is actually the inverse function. All right. Now, that's the inverse, but the question here says, well, is that inverse a function? So I want to remind you from Algebra 1, in order to test whether or not a function is an inverse or not an inverse, but in order to test whether or not it's a function in general, the easiest way that you can do that with a graph is to use the vertical line test. So if I did the vertical line test and I went through and drew a line, I'm trying to make sure. Okay, then does this vertical line pass through more than one time on that graph? No, it does not. Okay, it only hits it one time. Okay, so that would pass the vertical line test, which makes it a function. But if I had something like this, if it was like a sideways looking parabola, well, does that pass the vertical line test? No. Now, it might pass it at one point if I had done a better job, but not all the time. Okay, so that would not represent a function. So that's what I'm talking about with the vertical line test. All right. Now, one thing I do want to show you on this graph, and I'm going to try to do this where I can pick this up and move it. But if I picked this up and I moved it over here, all right, then that's what it would look like, okay, if I tried to put them together. So another thing that you need to know about inverses is that they are actually symmetric, okay? They can fold, all right? So they fold over the y equals x axis, so right here. So that will always be that imaginary like fold line. So you can kind of envision it folding diagonally and it would match up perfectly. All right, so that's another characteristics of inverses on graphs. So if you had two graphs on a paper, you could say, yes, that's an inverse because it has, you know, that symmetry over y equals x. All right, I'm not asking you to necessarily do that. I just wanted to talk about that characteristic. All right, so another example of inverses is if we look at this particular one, all right, then what are our points? So this point up here is -3, 4. This point over here is +3, 4. And then we have 2, -1. We have 1, -4. We have 0, -5. There's a whole lot of them, but it helps to, with this one, it's going to be a little easier if we plot more points. So -1, -4. And then -2, -1. Oops. -1, sorry. All right, so think about what happens if we flip-flop those, right? Remember, the x's and the y's do what? They just switch. So if I take this top point, I would have 4, -3. All right, and then I would have 4, +3. Then I would have -1, +2. I would have -4, +1. I'd have -5, 0. I'd have -4, -1. And then I'd have -1, -2. Whoops. -1, -2. All right, and I'm going to do the best I can to draw those points going through each other. It's not the prettiest. All right, but you get the point. All right, so that is the inverse of this original graph. Okay, the x's and the y's flipped. However, is that inverse a function? The answer would be no. And the reason why it's no is because does it pass the vertical line test? No. All right, and so that's why it does not represent a function. So this answer would be no. All right, now I want you to see that visually as well. Okay, so if I pick this up, and I move it to the other picture, then that's what it looks like. Okay, and I know it's kind of hard to see it there, but think about that vertical line test. Okay, so if I were to draw that y equals x imaginary, axis, pretend that I did a really good job, then hopefully you can envision that folding over and matching up perfectly over that y equals x axis. All right, so that is an example of our first learning target from page 22 and 23, I think, in your packet, where you are looking at inverses both in a table and on a graph. All right. All right. So the next thing you have is, can I find an actual inverse to a function? So if they give you a function and you have to do it algebraically, then these are the steps. And I've already kind of went through those, but we're going to swap x and y. We're going to solve for y, and then we're going to rewrite it in inverse notation. All right, so we're on page 19 in your packet. So for this first example, I would have, remember what I said about f of x, g of x, those are another way to say what? Y. So if I switch x and y, I'm going to have x equals 5y plus 3. Now the second step is to solve for y. So I'm going to subtract 3 from both sides. So I would have x minus 3, since obviously those don't combine, equals 5y. Divide by 5. And then I can rewrite that, but I'm going to go ahead, instead of rewriting that and just to rewrite it again, I'm going to go ahead and put it in inverse notation. So since this started out as f of x, we're going to put f to the negative 1 of x. That represents that it's an inverse, equals the x minus 3 over 5. All right. Now, depending on what you're doing with the inverse, sometimes it is helpful to see that in a linear format. So another way that you could rewrite this would be like, this would be like a 1, right? So another way that you could rewrite that would be 1/5 x minus 3/5. All right, and that's helpful because if I did need to draw that on a graph, pretend I didn't already have a picture, then I could use the y-intercept and the slope to help me draw that. All right, so either of those are acceptable. All right, another example, this is the same thing as y, so I'm going to switch my x and my y. So x equals 3y plus 1 over 5. So now I need to solve for y. Well, the first thing I want to do if I have anything in a denominator is go ahead and get rid of it. All right, so how do I get rid of that 5 in the denominator? Well, I can multiply this right side by 5 and it cancels out. But if I do that, I need to multiply the left side by 5 as well. All right, so now I would have 5x equals 3y plus 1. Now I'm still needing to solve for y, so I'm going to subtract 1 from both sides. So 5x minus 1 equals 3y. Divide by 3. I'm going to go ahead and write that in inverse notation. It was g of x, so g to the negative 1 of x equals 5x minus 1 over 3. If I wanted it in a more linear format, then I would have g to the negative 1 of x, inverse of x, equals 5/3 x minus 1/3, right? So that's if I need to see that y-intercept and all that in the slope. Okay, so again, either of those are acceptable. All right, a couple more examples. All right, so again, if we're finding the inverse, h of x is the same thing as y. So I'm going to switch x and y. And then I'm going to solve for y. Now, you have a couple of options here. The fact that this has a divide by 2, you can go ahead and multiply everything through by 2 to get rid of that denominator early on, or you can do it later. For me, it's a little bit easier to go ahead and do it right now, okay? Because I don't know about you, but I don't personally love fractions. All right, so if I multiply by 2, that means I multiply every term by 2, every term, all right? So now I'm going to cancel out this 2 and this 2 cancels, all right? But everything else does not. So that leaves me with 2x equals y minus 12. And it's already looking a little prettier. So we're going to add 12 to both sides. So 2x plus 12 equals y. But I'm going to rewrite that in inverse notation. So it'd be h to the negative 1 of x equals 2x plus 12. And that's our inverse. And it's already in a linear format. All right. The fourth example, again, we're switching this with y, right? Because this is the same thing. So now we're going to swap x and y. We don't have any fractions, so we don't have to worry about that. So I'm going to go ahead and subtract 6 from both sides. So x minus 6 equals 2y cubed. Divide by 2. All right. And then we have x minus 6 over 2 equals y cubed. Now, this is where people are going to get a little confused, okay? If it was squared, you would square root it. But this one is cubed, so we need to cube root it, all right? So to cube root it, it looks like this. All right. And when you cube root a cube, that essentially cancels out that cube. All right, which just leaves us with y. So to save myself a step, I'm going to go ahead and rewrite that in inverse notation. So I'm going to have g to the -1 of x equals the cube root of x minus 6 over 2. All right, and I could write that in a more linear format if I wanted to. All right, and it would look like this. I just like you to see it in different formats because you just really never know what you're going to see later. So this would be like a 1/2 x minus 3. And that's because this is technically a 1, so 1/2 with an x, and then -6 divided by 2 is -3. All right, so again, either of those are acceptable. All right, I wanted to look at a couple of more challenging problems with you. So these are actually in your practice problems on page 20, but I figured that you'd probably get to some of these and kind of, panic a little bit because they do get a little bit trickier. All right, so if we take a look at this, then again, this is y. So let's switch x and y. I totally messed up already, right? So let me fix my mistake. If y'all were in class, you'd be letting me know that out loud. All right, so I have my x and my y switched, but I do have a 5, right, in the denominator. So again, for me, it's easier to go ahead and take care of that from the beginning. So I'm going to multiply every term by 5. All right, so that will cancel this 5 and this 5. So that leaves me with 5x equals -4y minus 55. All right, and then I'm going to add 55 to both sides. So 5x plus 55 equals -4y. Divide by -4. All right, give myself a little more space. And so this cancels. All right, so I'm going to go ahead and write it in inverse notation. This was a what? A g. Okay, so that would be g to the -1 of x equals 5x plus 55 over a -4. And you could play around with your signs there to make that a +4 in the denominator. That's typically going to be ideal, but this would be acceptable. All right, another way that you could rewrite that in a more linear format would be a -5/4 x plus 55 over 4, or actually it'd be a minus because of the, whoops. Oh, my color's changed. Minus, okay, because a positive divided by a negative is a negative. All right, so that would also be acceptable. All right, last example for this video. All right, so again, I'm going to switch my x and my y. All right, and this time I have 2 numbers in my denominator. All right, typically I'm going to pick the largest one because that's going to eliminate all of my denominators. As long as they are, divisible by the same number at least, right? If this would have been a 5 and this would have been a 3, then I would have to multiply through by 15. Okay, but since 3 is divisible, or 6 is divisible by 3 rather, then I can multiply through by 6 and get the same thing accomplished. All right, so I'm going to multiply every single term by 6. All right, so this 6 right here cancels. All right, now over here on the right, you got to think, 2, like if we look at this, that's really 12 divided by 3, right? 12 divided by 3. So that's really 4. All right, that's really 4. All right, so I'm going to kind of rewrite this and pretty it up because that's a hot mess, right? So I'm going to have 6x equals y to the 5th plus 4. Now I can subtract 4 from both sides. So 6x minus 4 equals y to the 5th. Well, just like before, if we had a cube root or cube, we did a cube root, right? Well, here we have a 5th power, so that just means we're going to do a 5th root on both sides. And remember that essentially cancels out your fifth root, right? It cancels that out, leaving you with the y. So in inverse notation, this was f of x. So I would have f to the negative 1 of x equals the fifth root of 6x minus 4. And I'd be done. All right, so I'm going to save the last part of this lesson, which is verifying inverses, so that we can do that in a different video because it's just too much. All right, so let me stop this video, and then you can start with the next video after you do a little bit of practice.